it's just a chance differences. So we can use that as well. So our formula now can help us do many things. I'm going to show you a couple of other sets of data moving forward on this. Let me see what I got here. Okay. Okay, I got one here that is arsenic and well water. I guess it was about 30, 40 years ago. I don't know if it's the UN, but there was some organization that was providing pumping stations and wells in India to remote communities in India that had problems with waterborne diseases because they were using surface waters. They're using streams and waters and very shallow wells for a water source. So they had all sorts of problems with waterborne diseases, typhoid, so on and so forth, cholera, and it took an enormous toll. So they figured that, gee, if we provide these communities with a mechanism for getting deeper, for digging deeper wells and pumping the water out of the ground, then that will reduce the rates of disease from that source. And in fact, they're very effective at doing that. Unfortunately, these same areas had very high levels of arsenic in the mineral beds in the ground. And what happened is they replaced one hazard with another hazard. They were finding many people were experiencing issues with arsenic poisoning, and that can cause all sorts of skin issues and lesions and cancer and so on and so forth, and literally replacing one issue with another. So it's important to us to know, well, where is that going to be an issue? And one particular study, this one, actually, this is probably real data. I don't remember where we got it from, but this is probably real data. It tried to correlate the depth of the well to the amount of arsenic that was in the water that was being pumped out of the well. That's practical information because that means that you can focus on going back to the communities that have the deepest wells and test them first and remediate them first, and then work your way up. And where you might want to start testing and so on and so forth. So it would be important for us to know the relationship between the depth of the well and the amount of arsenic in the water coming out of the well, if there indeed is a relationship. So we have two sets of numerical data. We have, what do we have here? We got the location, the name of the town, well ID, and so on and so forth. We have the depth of the well and the amount of arsenic. We have numeric data in the form of the depth of the well. We have numeric data in the form of the arsenic. And if one of you guys want, you can actually use this data for a project or something like that, if one or two of you guys want. Okay, so, and I think you might be able to get more data than I have there, but let's take a look at how we might analyze this. I believe I have this as SPSS file also. So I am going to, I guess I don't. Well, I had this all. I'm surprised I don't have that way. I'm going to save this on the desktop and I'm going to import it into SPSS. I think I pulled up the wrong folder there because I know I set all this stuff up. Okay, no problem. Oh, I needed to look at one other thing here. The top row has the variable names. So I just wanted to check that for sure because SPSS is going to ask me that. So file, open, data. I'm going to go to the desktop. I know it's an Excel file, so I wanted to look for Excel files. And here's arsenic and well water. I'm going to click open. And it's A1 through H329. That sounds right. And the variable name is in the first row of data, so I'm going to leave that checked. I'm going to say OK. So it's going to import this data. So you can use programs like databases, Excel to organize the data and then import it into SPSS. Perhaps for whatever reason, I want to keep this private. So I don't want patient names. I don't want town names even in here. So I am going to highlight the subdistrict. I'm just going to put the well number, which doesn't only identifies it for me. I'm going to highlight these next four boxes, and I'm going to say delete. Clear. They're gone. I'm also going to say, I don't need to know the year. I'm going to delete that too. Now, here I am now. I could also delete the well ID if I really wanted to. My analysis, I probably don't care, but I'm going to leave it there for our purposes. So now I only have the variables I need to work with. Now, and I'm giving this to you as a hint, if you're going to work with that community health survey, right, you got 75 variables over there. It's kind of unwieldy going through all that data. You can eliminate all but the variables that you want to work with, okay, to make it more manageable. Then save it under a new name, and you still have the original file, but you also have a manageable data set. Okay, so you might want to do stuff like that as you go through it. Now there is some numerical data in that survey. I think there's some weight, height, that kind of stuff. At a minimum, there might also be some other numerical data, right? So you might, if you're going to do, if you're going to do analysis, if you're going to do this kind of stuff using that data, you're going to want to be working with numerical data, not categorical data. Okay. However, there's other files that we have that have lots of numerical data. You might have noticed I posted data from the Framingham study. That's that study that involved doctors that followed them for 30 or 40 years that involved heart attacks. There's a digitalis study that involves, I think they tracked heart patients that were using what's digitalis? Is that to regulate heart rhythms or something like that? Or how do they use digitalis? Anybody know? I think it's some sort of heart rate regulator or something like that. But at any rate, we're looking at this right now. Okay, so now I want to know if there's an association. First way I look at that, I'm going to go to a graph, legacy dialog, scatter. Let's scatter plot all of these different points and see if it looks like there's an association. I don't care. I'm not going to use well ID. I know that. So I'm going to put, just for the hell of it, depth in X and arsenic and Y. I'm doing it that way because I know later on I'm going to be doing that in regression. I don't really need it in a particular order to evaluate correlation. I'm going to click OK. It's going to plot it for me. What does it look like? Well, it's kind of funky, isn't it? The reason why it's kind of funky is because many of the wells at any depth, they're just in areas where you don't have any arsenic in the water, right? So that's a little tougher now. I'm going to see this line that it might plot and see if it looks like, let's see, as the depth goes up, right, it looks like the arsenic level actually goes down, right, a certain range. Could be that maybe for a while it goes up, then for a while it goes down. I'm not sure. But from here, it looks counterintuitive as the depth goes down. But that's starting at anybody know why we're talking about why we're not starting at a lower number than say 25 or 30 feet, right? Because most of these wells are wells where you put the pump down in the bottom and you pump up. A 32 feet, you can have those pumps with the handles, where you suck water up, right? You prime them and you suck water up. They'll only work up to 32 feet because that atmospheric pressure is 32 feet. Anything over that, if you try and pump, you get a vacuum, right? Because you can't pull water up. So the only way to pump it is to put a well down there and pump the water up, right? So these are all wells that work like that. That's why they don't have anything shallower than that. So at any rate, looks interesting, but I'm not sure what to make of this. Okay, so I am going to next go into analyze, correlate bivariate, and I'm going to move depth and arsenic into here. I'm going to say OK, and I'm going to see if there's a correlation. Well, it says negative 2.45. That tells me that there is a correlation. It's different than 0, and my significance is very low, so it's a real correlation. And it's a downward slope. As depth goes up, arsenic level goes down, apparently, in this data set as a whole, right? And so I seem to have some sort of correlation here. So now I'm going to go to regression. Regression, linear. I'm going to do the same thing. My dependent variable is the depth. My independent variable is depth. My dependent variable is arsenic level. I'm going to click OK. Now look, there's our R value. Our correlation is 0.25. Our R square is 0.06. What does that mean, that 0.06? The way that we interpret this data, 0.06, that number, that R squared, can be interpreted as the as an indicator of how much the variability in one variable impacts the variability in another. So in other words, this is saying only 6% of the change in the arsenic level is due to the depth of the well. So even though we have a significant correlation, statistically significant correlation, it doesn't seem like an important one because 94% of how much arsenic is present is caused by other factors. So just because you can get a correlation doesn't mean it's a useful correlation. Now, I think that one of the issues here is that a lot of this data is in locations where you have little and no arsenic. So it's confounding a lot of this information in terms of like it's masking a lot of the other uh, 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 effect that we're finding. And you might do things like maybe try and filter it so you're only looking at the highest levels of arsenic and seeing whether or not in those areas where you have the highest levels of arsenic, that there's a correlation between the depth in those areas. And so, in other words, eliminate all the wells that have very little arsenic. But you can play around with the data a little bit. Let me take a look at another one. Maybe it'd be a little bit more fruitful. Okay. Okay. Let's see. Violent crime. Let's take a look at this one. So these are a few examples of data sets. This is violent crime in different states and the rate of along the murder rate, number of violent crimes per period of time, whatever it happens to be, murder rate, the poverty rate, percentage of families that are living in poverty, the high school graduation rate, college attendance rate, percentage of families, single parent families, the unemployment percentage at the time this study was done, and whether or not it was some measure of whether it's a metropolitan area or not. Maybe that's a density, population density, or something like that. So let's take a look at a couple of these things that we think may impact each other. Perhaps there's some association between the poverty rate, state by state, and the murder rate. Okay, let's take a look at a scatter plot. First thing I'm going to do is plot it so that I know whether or not I want to chase that particular association. So let's see, I'm going to say, what did I say? Poverty rate and murder rate. And I'm going to say, okay, and let's see what our plot looks like. Well, hang on a second. It does look like there is a bit of an association here, right? But what do I see here? What's going on in this thing that's unusual? Anybody see it there? There's an outlier there. There's some value that's just completely different than all the other states for some reason. Okay, and let's see what that is. That happens to be a place where the murder rate was 50, where everything else was under 20. Let's go back to the data and see where that might be. Okay, let's see where we see a murder rate of, here we go, 41.8. What a surprise. It's our nation's capital, right? I'm going to delete that data. I'm going to remove that. There's other more elegant ways of removing outliers in SPSS. I'm going to do it quickly now by just highlighting that row and deleting it. Let's take another look at that. Now, who knows why that was? Maybe during the period of time that this was going on, there was some sort of mass murder in Washington, D.C., or you can imagine what the statistics would look like if you look at the annual murder rates in New York City in 2001. Because during normal year we have about 5,000, what is it, 5,000 murders in New York City? Maybe not even that many these days, but you have several thousand. In 2001 we had over 3,000 in one day, right? And 9/11. So the statistics, if you look at New York City during that year, are grossly different than other years. So you might eliminate that data, because it's an outlier, it's an unusual situation. Okay, so I'm going to analyze this data. I'm going to go in, I'm going to try this again. I'm going to do my scatter plot again. Okay, and I'm going to still set up, except now the date is different. And, whoops, I thought I eliminated that. Oh, there it is. Now take a look at it. It looks quite different now, doesn't it? And we can see that there's apparently a correlation here. I'm going to just plot that line. Okay, and there it is. There's our correlation, right? Now look over here, R squared actually calculates R squared. Remember I told you that that represents what portion of the change in the murder rate can be attributed to the poverty rate? Well, it's 18%. It's almost 20%. Now we're getting into something that's a little bit more significant. There's other factors, right? Remember multiple regression, we look at many factors. But for now, identifying something that causes 20% of the increase in the murder rate, that's pretty significant to us, I would think. Okay, so let's see how significant this is. I'm going to go into analyze, correlation by variate. I'm going to move in murder rate, and I'm going to move in poverty level. And you can look at the other factors as well, unemployment rate, for instance. Okay, and let's see, our correlation is 0.427. It's far, and it's significant. It's far away from zero, not one, but it's a positive correlation. As the poverty level goes up, murder rate goes up. I'm going to analyze through our regression now. Regression, linear. Okay, I'm going to put my independent variable, which is my poverty rate, or at least I would imagine it's poverty rate, and my murder rate up here. And I would actually go ahead and do my calculation. And I find a significant level of association. My R square is 18. 18% of the change in one variable can be attributed to the other variable. And I have my numbers here, where if I don't know what the murder rate is in a certain population, but I do know the poverty rate, I can see if there's an association. Also, I can see that for a certain change in the poverty rate, what kind of change I should expect in the murder rate. Get it? So in other words, if I take this formula that we've just created, okay, let me get my notepad. Okay, let me make my formula up. Oh wait, am I okay behind me there? No surprises, right? Nothing popped up. Okay, y is equal to alpha plus beta x. Y is equal to alpha is 0.432. Remember that top number is my y-intercept plus 0.365 times x. So now not only can I use this as a predictor of the murder rate given a certain poverty rate, but I can also say to myself, gee, if I can reduce the poverty rate by 1%, I can see what kind of impact that's going to have on the murder rate. Okay? Whether or not that really works or not, or it's effective or not, who knows? But now we have a way to compare it to the unemployment rate or some other factors. Which one has more influence on the murder rate? Which one will a certain change in? Which one it can be expected to produce the most benefit, and so on and so forth. So this linear regression correlation is tying together is valuable to us because it helps us to understand the relationship, not only demonstrate that there is a relationship, but help us to understand how we can allocate resources or make changes that will have positive outcomes on the variable that we're interested in changing. Okay, so I think we should stop there at this